rates of reaction in light of the ideal gas law. Whenever we have variables and they're multiplying each other beside each other here, this means that they are inversely proportional. This volume here for a gas is inversely proportional to the amount of pressure exerted by that same gas. If they're dividing on top of each other, this means that they are proportional. As you can see here, they're dividing by each other. This means that they're proportional. So if you put them all together, you get a combined gas law. And then we're also going to be adding that with Avogadro's law, and we put them all together down here. So as you can see, my P1 is obviously stuck here with my V1, so I'm going to keep that over there. My T1 is by itself, but remember, we cannot forget the N1 in Avogadro's law. So I'm going to bring that down. That's also under N1. I'm going to mirror it on the other side, so I have P2 times V2 over T2 times N2. However, if a gas conforms to the molecular kinetic theory and follows gas laws perfectly, by the way, this here is impossible. However, we do it for calculations just to make it easier, just for simplicity purposes. And then we're just going to use R as our value to depict that. So instead of just my here, I'm just going to make it into a general formula where it's just P V over NT instead of 1 or 2's. So then eventually, to get my PV is the nRT formula that we're familiar with, I'm going to get my NT, I'm going to times it by NT on the right side. These cancel out. If I do it on the right side, I need to do it on the left side. Then for my R, as to how I got this value, please see my 20-minute video as to how I got that. This question over here, I have 0.5 grams of Na. However, I need to change it into moles because I always want to do it in moles, not grams, and then eventually get my moles of Na in seconds. Now I'm going to use my formula here, and I'm just going to use my H2 given values in order to put it into here, because I'm trying to find my rate at which H2 is generated, not Na. So I'm going to be using those values. I brought it down. So this one is over here. My volume, I have no idea what it is. I'm trying to look for it in liters per second. So that's what I'm trying to find. I'm going to leave it isolated. My N, I have no idea what it is because this is in moles of Na. I need to find my moles of H2. So I've done it over here. I figured that out. So eventually this needs to go here. For my R, this is constant from over here. It's just going to go in. So I'm just going to put that there. And then for my K, I have 30 degrees Celsius. I need to change it into K. See my 20-minute video as to how I did it. I'm going to convert it into 303.15 K. And then I'm just going to put it all into this formula here. And remember, this one goes into here, my moles of H2. And then eventually this here needs to isolate. My V needs to be alone. So I'm going to divide this side by 102.4 K. If I do it on this side on the left side, I need to do it on the right side, as you can see over here. So then I just isolate. Moles cancels out, kPa cancels out, my K cancels out. So I'm just left here with my L. So I'm just going to be giving this answer over here. For my reactants, if there's a lot of reactants colliding on the very left side, this means that there are no products here on the right side. This means that there's a lot of collisions. There's a whole party going on here. However, if there's less reactants now, because some of them went over to the products, now I have less reactions happening, not as fast of a rate, because I have less here, because some of them have gone over here. So hopefully this helped. Please pause the video and try this yourself, and I'll be giving you the answers shortly. This here is the answer.